Hello, I welcome you all in this course of mechanical measurement systems. And today we will start with, we'll continue with the discussions on first order system. And today we will discuss the ramp response of first order system. So, first order system. System or systems, and we'll go with the ramp response. These are the typical outputs like step input and ramp input. This is the typical input to any measuring instrument of any order. So, right now we are discussing the first order system. So, ramp input to the first order system. So, ramp input to the first order system is going to be like this. This is output, this is input, time, this is time, and this is Qi. This is not output, this is input, Qi, time, and then in step input, it was like this. But here, the situation is different. Here, the input is a ramp input. The ramp input means the input is changing with time. There is a ramp. So, for any particular time, you will find altogether different input. Now, I can give you one example of this type of input. Suppose in a vessel, the water is being heated, sensible heating of water. So, water is being heated, the water is available at the room at 25 degrees centigrade, and then the water in the container is heated, the temperature will start rising, and in certain time interval, depending upon the quantity of heat supplied and quantity of water available in the pan, the temperature will rise to, let us say, 80 degrees centigrade. The boiling has not yet started. The moment the boiling is started, the temperature will become constant. So, during this sensible heating, if I am putting in one thermometer, so the input of the thermometer is changing with time. In step input, the water was already at 800, the case of step input is like this, the water is already at 800 degrees centigrade, atmospheric pressure temperature is 25 degrees centigrade, the thermometer is taken and it is simply put into the water. That is step, and here the step is input is going to be theta I 80 minus 25, it is 55 degrees centigrade. And then we will study the step response of the system by using the formula theta O is equal to theta I 1 minus e raised to power minus t by lambda for a step input. But here in this case, this is not constant. This is varying with time. This is varying with time, right? So, and rate of heating becomes very important here. From 25 to 80, in how much time? In 8 seconds or 80 seconds or 800 seconds? That will decide the rate of the loading, right? And vice versa. If we have the rate of the loading, we can find the instantaneous input to the system. Suppose it is going from, for the sake of convenience, let us take 0 to 80. Temperature is put in the vessel. Initially, the bulb was at 0 degree centigrade. Water was also at 0 degree centigrade. It was all water, not ice. No ice was there. If ice is there, then it is a different story. All water at 0 degree centigrade, and now we have started heating the water, and temperature of thermometer started rising. Right? If we are attaining temperature 80 degrees centigrade in 80 seconds, then input rate is 1 degree centigrade per second. If we are attaining 80 degrees centigrades in, let us say, 400 seconds, so input is 0.2 degree centigrade per second. If 400, 80 by 400. Yes. So these two rates are different. For these two different rates of input, the response of the system will also be different. It is obvious, right? Chances of error in this case is higher than the chances of error in this case. But we have to quantify all these things. By perceptions, we cannot take any decision. So we will do certain mathematical analysis, and again we will start with the basic equation. Now the basic equation is Qo is equal to Qi 1 minus e raised to power minus t by lambda. This is the basic equation for first order system. Yes, here we have to multiply by sensitivity also. Qo is equal to k Qi. Fine. Now Qo is equal to Qis is equal to 0 at t is equal to 0. Initially both are 0, right? And input to the instrument, input to the instrument is rate multiplied by t. Suppose rate of input is Qis dot. So instantaneous input to the instrument is Qis t. So for t is greater than 0, we can always say the input to the instrument is Qist. Output we do not know. Output we have to find using this equation. Now this is for first order equation. This is not for this. This generalized equation for first order system is lambda d plus 1 Qo is equal to k Qi. Now here the Q input is instantaneous input. This is instantaneous input. Now here again we have to find first of all this complementary function. So Qo complementary function is going to be equal to at t is equal to 0, okay, so is going to be equal to again lambda d plus 1 is equal to 0. So d has one root, that is minus 1 by lambda. So again it is going to be c e raised to power minus t by lambda, as we did in the case of step response. Now regarding the particular integral, particular integral is going to be k Qist 1 minus lambda d. Okay. Now we can further manipulate this equation Qis, this is rate, and here t minus lambda, this dt. Now this dt is dt by dt. So this is going to be equal to 1. So particular integral here in this case is going to be k q dot is t minus lambda. So now we will add these two, complementary function and particular integral, and we will get the final expression. The final expression is Qo is equal to c e raised to power minus t by lambda plus k Qis dot t minus lambda. Now here again we will put the initial condition. The initial condition is at t is equal to 0, output is 0. So this is 0. When we are putting t is equal to 0, this will become c plus k q I s, and then it is minus lambda, because here t is 0. So we will be getting the value of c as k q I s lambda. Now by putting this value c here in this equation, we will be getting qo is equal to k q I s lambda e raised to power minus t by lambda plus t minus lambda. This is the response equation for ramp input to first order system. Again, for this we will have to estimate the error also, because the instrument which is responding to this input shall not follow this line, it is obvious. But here we have to quantify. So in order to quantify that, we will calculate error in the measurement. Now for doing this, error in the measurement, we can take qi input minus qo by k. This is input, actual input minus input indicated, because ultimately we are output of the instrument is also showing input to the instrument, right? So this qo by k will give you the actual input. Now when we are doing this, we will get qi is qis t, right, minus this is qis, and this is also dot, this is also dot, right. So it is equal to qo by k. So minus qis dot lambda e raised to power minus t by lambda plus t minus lambda. Now here this qis t will cancel this, and we will get the final expression as error in the measurement is equal to minus qis lambda e raised to power minus t by lambda plus qis lambda. This is error in the method. This error has two components. One component is this one, which is time dependent. Another component is this, which is not time dependent, which is dependent only on the constant, time constant and rate of input. That's it. It is not dependent on anything. So this is time dependent, or it is a transient error, because it's a function of time, and this error will change with time. If the value of t is infinite, this is going to be 0. So after a certain time interval, this error will diminish. But in any case, we are going to have this error through the entire measurement process, right? And if we draw the response of this step input, the ramp input, response of ramp input, then we will get a curve like this. Initially, it is going to be like this. So this change in the, because this is a straight line, these are parallel to each other, right? So we are getting this due to presence of this factor. And after a certain time interval, this factor diminishes and we get only qis lambda, and that is this one. Now error in measurement. So at a particular time t, Now at a particular time t, here, this is the error in the measurement. This is the response of the instrument. So instrument is showing this much of input and actual input is this one. So this is the steady state error, and this can be expressed as Qi s multiplied by lambda. Right? And for example, this reading we are getting at T1, but actually this is going to happen for the instrument, it is going to be at T2. So this time interval is known as time lag. So there are two things: steady state error at a particular time, actual input and output of the instrument. This difference is steady state error, and it is shown by QIS lambda. And time lag means actual input is this, and the instrument will be showing actual input after time interval of delta t. And this is known as time lag. There are two things, and this measurement during this time interval has to be avoided because it will creep in, because because the variation is not linear. So what time we are making the measurement, it is important here. But once this transient part is diminished, anytime we can have the measurement, and we are going to have a constant error, that is Q dot is, that is rate of loading multiplied by time constant. Now regarding this error in measurement, in this graph, the same thing is shown here in this graph. This is error in measurement divided by error in measurement at steady state, and this is increasing, and it is the ratio is attaining at the value, a value of 1 at approximately t by lambda is 0.5. Is not, it is not t by lambda, it is t only. So at after 5 seconds. Right now, after this we can take one example. Now this example states that temperature sensitive transducer is used to measure the temperature of a furnace, and it has been idealized as first order system subject to RAM input. So a temperature sensitive transducer is used to measure a temperature of a surface furnace. There is a furnace, and it is idealized as, or it is considered as, first order system subjected to ramp input. So first order system subjected to ramp input. Right? Calculate the constant of transducer if the furnace, time constant of transducer, if the furnace temperature increases at the rate of 0.15 degree centigrade per second. So furnace, there is a furnace, the temperature of the furnace is rising, and temperature of the furnace is rising with a rate of 0.15 degree centigrade per second, and the maximal permissible error is 4.5 degree centigrade, and we have to find time constant. So maximum permissible error in the measurement of the surface temperature is 4.5 degree centigrade. So error in measurement, this is steady state error, is Q dash is lambda. There is a very simple formula, and error is 4.5 degree centigrade, rate is 0.15 lambda. So lambda has to be 4.5 divided by 0.15 is equal to 30 seconds. So time constant of a thermometer has to be 30 seconds if we want to confine the error in the measurement as 4.5 degree centigrade for a temperature rise of 0.15. Suppose the rate of temperature rise was instead of 0.15 it is 0.45. Or let us say 0.2. Instead of 0.15, it was 0.2 degrees centigrade per second. Now, what is going to be the error? Time constant is given 30 seconds. So, it is going to be 6.0 degrees centigrade. QIS multiplied by lambda, it is 0.2 into 30, 6 degrees centigrade is going to be the steady state error in the measurement. So, we have changed the rate of change of temperature, the error has increased. Similarly, if you reduce it to 0.1, when we reduce it to the 0.1, the error will be reduced to 0.3 degrees centigrade. Because error in the ramp input, error in the measurement is a function of this rate of input multiplied by the time constant. Okay. So, another example, we will take one more example, which is you will find more interesting. A weather balloon carrying a temperature sensing device with time constant of 10 seconds. So, they are weather balloons to find the temperatures at high altitudes. So, there is a weather balloon which has a temperature sensor and it has time constant of 0.15, sorry, what is that? Time constant of 10 seconds. This is the time constant for weather balloon, and the balloon is rising. The speed of rising the balloon is 6 meters per second. So, there is a balloon and balloon is fitted with a temperature sensor and it is moving vertically with a speed of 6 meters per second. The balloon transmits information about temperature and altitude through radio signals. Okay. At 3000 meter height, a temperature indicated is 35 degrees. So, 3000 meter height, x is equal to 3000 meters or 3 kilometer from the Earth's surface. The temperature indicated is 35 degrees centigrade. Right. Determine the true altitude at which 35 degrees centigrade temperature occurs. We want to have x1 and x2, that is true value, true height at which this temperature is, because the signal we are getting, it has some error or it is a sluggish signal, right. So, it has some error and that correction has to be made in the measurement. So, we have to find at when the balloon is at 3 kilometers above the surface, it has sent one signal indicating temperature 35 degrees. But is it really 35 degrees centigrade? Because temperature sensor has certain error in the measurement, right? And it is a steady state error. It may be presumed that a temperature sensing device is of the first order and the temperature varies with altitude uniformly at 0.01 degrees centigrade per meter. Temperature is changing, right? Now, here the temperature is changing with distance. This is not the rate of input. In order to find the rate of input, we have to multiply these two and then we will be getting 0.01 multiplied by 6, 0.06 degrees centigrade per second. Variation, because temperature, we have to find temperature variation with respect to time. Now, we have replaced velocity or distance with time. Now, we will talk in terms of time because distance is given, velocity is given. So, we can always talk in terms of time and time lapse in the measurement indicating the value. So, input is QIS is 0.06 degrees per every second. This is going to be the change in temperature. Lambda is 10 seconds. So, steady state error here is going to be equal to how much? 0.06 multiplied by 10 is equal to 0.6 degrees centigrade. This is going to be the steady state error. Now, once we have this steady state error, we can simply find the value of x. Now, the x is this is 0.01. Okay. So this is 0.6. 10, okay. QIS and QI degree centigrade. Okay. So this is error in measurement is equal to QIS into lambda. Right? And here, because QIS we have taken 0.06, lambda is 10, it is 0.6 degree centigrade. Now this 0.6 degree centigrade, when it is divided by 0.01 degree centigrade per meter, we will get the value of x or x3. That is going to be how much? 60 meter. Sorry, 60 meter. 60 meter. So actual height of the balloon when the signal was sent was 6,000 minus this error 60 is equal to 3,000. It is so actual height when the signal was sent. The actual height when the signal was sent is 3,000 meter. 3,000 meter minus this error minus 60, and it is going to be 2940 meter. So the temperature indicated as 35 degrees centigrade is not at 3000 meter altitude, it is at 2940 meter altitude. Now we will take another example. The statement of the example is a position control system has time constant 0.2 seconds. So time constant lambda is 0.2 seconds. It is for position control system. The input changes with a constant rate of 5 mm per second, right? From zero position, from initial position is 0. Calculate the error after 0.4 seconds and steady state error also. So steady state error, first of all let us calculate steady state error. So steady state error is steady state error is QIS dot lambda, and QIS is 5 mm per second, that is ramp slope rate of input. So 5 mm multiplied by time constant 1 mm. This is steady state of error. So this instrument will give error of 1 millimeter for a ramp input of 5 millimeters per second. Now error at t is equal to 0.4 seconds. And if you look at the time constant, it is 0.2. So error at total error is transient error plus steady state error, and we can always write minus QIS lambda e raised to power minus t by lambda plus QIS dot lambda. This is the total error. Steady state error we have already calculated, it is 1. Now for this transient error, minus QIS is 5 mm per second, right? And lambda is 0.2. E raised to power minus t by lambda, t is 0.4. So e raised to power 0.4 divided by 0.2. And this is again minus 1 e raised to power minus 2 plus 1, or is equal to 1 minus e raised to power minus 2. And when we take 1 minus e raised to power minus 2 plus 1, and it is going to be equal to 1.135. So after 4 seconds or 2 times of lambda, the error is 1.135, right? And finally steady state error is 1 mm. So I think we should conclude this here itself, right? And we have amply gone through the step response and the ramp response of first order system. In the next class, we will start with the impulse response of first order system. Thank you.